All right, guys, so we have seen both slinky waves, we've experimented with slinky waves, we've studied ocean waves for a little bit. Now let's discuss changing the properties of those waves and what that does to the energy. Remember our focus question. We were talking about what is the relationship between wave properties and wave energy. And wave properties, what we mean by that is the wave's frequency, the wave's wavelength, and the amplitude. So if we change those things, what does that do to the energy? Those are the questions we need to answer. So this is where you take your definition from the discussion post yesterday and you post it into your guided notes. You do that by copying and pasting Mrs. Mott's definition into your guided notes at this time. So how can we define energy? Find that post and copy and paste it to your guided notes. So we're going to ask two new questions. Which had more energy? High amplitude waves like this, or low amplitude waves like this? Which has more energy? High frequency waves like this, very frequent, or low frequency waves like this, not very frequent? We're going to try to experiment a little bit more with that same cord, slinky, or rope, and try to feel in your own arms what requires more energy in these two situations. So if we're going to test, let's say, just amplitude, we're going to test just amplitude, then we have to keep all the other variables the same. What I mean by that is if I'm going to change the height of the wave and how high waves versus lower waves, what the energy is like in both of those, then I better keep the frequency the same. I need to keep the frequency the same while I'm keeping high and low amplitude. I do that by keeping a constant rate or rhythm, like 1 and 2 and 3, and never speeding up or slowing down, but keeping the same beat. Take a look in the next video. High amplitude versus low amplitude. Which will require the most energy if I keep the frequency the same? High amplitude. Low amplitude. High. Low. Stop. Which required more energy?
High amplitude.
Hopefully you tried this out for yourself, but which had more energy in the video? The one that was creating high amplitude waves or low amplitude waves? The ones where the peaks were really high and the troughs very low, or vice versa? What evidence do you have that high amplitude waves have more energy? And there's that question again. Can energy be created or destroyed? Now we're changing up the variable. How can you control all variables so that you're only changing frequency this time? The wave maker is going to create high frequency waves and low frequency waves. So waves that happen very often and waves that happen not so often. And I want you to compare the energy needed to make these waves. In this one, you will see there are two lemons on the table. We're not going to change amplitude at all. We are going to this time change just the frequency of the waves. So high frequency waves versus low frequency waves. Okay, ready? High frequency. Low frequency. High frequency. Very high frequency. Low frequency. What required more energy?
High frequency.
Again, hopefully you've tried this yourself after watching the video, but which had more energy? High frequency or low frequency? And what's your evidence that high frequency waves have more energy? So it's probably not very shocking that high amplitude waves have more energy than low amplitude waves. This isn't shocking because if you've ever stood in a lake or an ocean and are hit by a taller wave, you can feel the force upon your body versus a low lapping wave on the shore. It is also not surprising that high frequency waves have more energy than low frequency waves. After all, they're coming by more often, therefore they're carrying more energy. Last variable to discuss. Which has more energy? Waves with long wavelengths or short wavelengths? Here is a wavelength with a long wavelength. Here is a wave with a short wavelength. Which do you think will carry more energy? So looking at the two different experiments there, the top experiment is when we changed amplitude. You can see that the peaks are very high or very low versus very short. And you heard that to make the higher amplitude waves, it required his arm to create more energy to move it, to create higher peaks, just like a large ocean wave would knock you off your feet. Then in the second experiment, I asked him to keep the amplitude the same, so it wasn't higher or lower waves, but this time more frequent waves, like in this one, or less frequent waves, like in this one. Notice again that their crests and their troughs are about the same height. It's just one is more frequent than the other. And you heard his testimony that it required more energy to create more frequent waves. So if I have higher frequency or if I have higher amplitude, I have more energy in these cases. What happened to the wavelength when I had more frequent waves? What happened to this wavelength right here? The waves got a lot shorter. So I wonder if wavelength is smaller, then frequency has to be larger. Stay tuned for a mathematical equation that'll help us out. Did you try it? Waves with short wavelengths are associated with high frequency, and we already know that high frequency waves have more energy. If I have shorter wavelengths, they come by more often, frequency, and therefore have more energy. Waves with long wavelengths are associated with low frequency. Long wavelengths mean low frequency, and after all, if they're not coming by very often, then they're going to be lapping long wavelengths, nice and gentle. They carry less energy. You mathematicians out there will like that all of this can really just be solved with a mathematical equation. Here's the mathematical equation. V, or remember that means velocity, which is also sometimes just called speed. Okay, V equals lambda, which remember means wavelength, times frequency. So I asked you lots of questions. If I increase wavelength, what happens to frequency? If I decrease frequency, what happens to wavelength? And all of that can be represented with this equation. Now, you know in multiplication that if I increase one side of my multiplication problem, then the other side must decrease. If I increase wavelength, then frequency is going to decrease, and vice versa. If I decrease wavelength, then the frequency increases. It has to mathematically, because I'm multiplying, if I want to keep the same velocity, that is. So, again, if I increase wavelength, then frequency must decrease. If I decrease frequency, the wavelength must increase. It's an inverse relationship, which is one of your vocabulary words today. Excuse my dog's panting and drinking his water. Here's a simple example. Let's say I've got a wave that is moving at 10 meters per second. That's its speed. Okay, so that's its velocity, its speed. And let's say that my wavelength is unknown, but my frequency is 5, I don't know, cycles per second. Okay, so 5 cycles per second. What does my wavelength have to be? My wavelength must be 2 meters times 5 cycles per second. So if my frequency is known, I can find my wavelength. But let's say, for example, if I made my wavelength 5 meters, then what does my frequency have to be? My frequency has to be only 2 cycles per second. So notice what happened there. If I increase the wavelength, then my frequency must decrease. This is an example of an inverse relationship. It is now time to update our vocabulary inside our guided notes. These 5 are the following vocabulary words. Please take time to look in your glossary, write the definitions, and draw a picture. Thank you for listening. Did you answer the question? What is the relationship between wave properties and wave energy? If I change wave properties, how does wave energy change?